Okay, let's come back to the discussion about the representative convergence. So last time we were discussing some kind of techniques in terms of like how we can do some kind of the conversion across the some 3D representations. So what we have seen last time is that basically for some of the representations here, as you can see, like for the conversion from the implicit function to the voxels, to the mesh to the point cloud, or the mesh to the multi-view images, actually those conversions kind of like very straightforward. Like basically we know how we can do this kind of conversion. The question was that how we can basically make some kind of the missing the bridges across these representations, like for the conversion from the point cloud into the implicit function, and also from the voxels to the mesh. So we are discussing some kind of techniques in terms of how we can build some kind of bridges, missing bridges here. So what we started discuss last time was basically about the conversion from the point cloud into the implicit function. So we discussed the bunch of the ideas for that. The simplest kind of the idea was basically fitting some kind of the polynomial the function. But the problem is that the whole shape cannot be represented with the polynomial the function, a single the polynomial the function. So the basic idea was that we are basically locally approximating the surface, basically the local surface, using some kind of the weighted the sum of the least squares, the equations. So that is basically the idea about the moving least squares. Basically, we are basically fitting the polynomial the function into the local the surface, basically finding some kind of the best parameters here. And the problem like finding these best parameters with respect to minimizing the weighted least square was basically the equation that is formulated as solving the eigenvector problem. So what we have seen last time is that after basically all the derivation, actually we could see that the least square problem turns out to basically just finding the eigenvector, which is corresponding to the smallest the eigenvalue for some kind of the matrix that we are calculating with the given the information. So this was kind of like the simple idea in terms of like fitting the polynomial function. And this idea also could be used to basically estimate the surface normal as well. So the surface normal is basically the information that is basically being used in the many applications, and also kind of some extra information, geometry information for the encoding some kind of the tasks, and also for rendering of the point cloud, and also for the more accurate 3D reconstruction as well. So actually also this moving least square technique could be used to basically estimate the surface normal. And also the surface normal also can be obtained from the kind of the other kind of cases from the scanning for the many other kind of the aspects. And the other technique that we also discussed last time is that when this kind of the surface normal information is given, either like by estimated using the moving least squares or some kind of the other kind of things, then using this information, the extra information, we could consider basically approximating the entire shape by using some kind of implicit function, which is obtained by solving some kind of the global optimization. So this was the another idea, which was called the radial basis function, which is basically representing the implicit function as the weighted sum of the radial basis function with our choice of the radial basis function, right? So here the question is that how we can find the optimal weights for each, basically the radial the corner defined for each of the point. So basically, as we have some like n number of the points, we are basically having some the weight for each point. So how we can basically find the optimal weights was basically the problem here. So the thing is that if we only solve this problem with the given the points sampled over the surface, the trivial solution basically becomes zero. Basically, assigning zero to all the weights is becoming the solution, which is basically satisfying the condition that the signed distance function should be zero at the point sampled over the surface. So to avoid this kind of the trivial solution, what we can do is that we are basically adding some kind of the additional constraints in terms of basically taking some kind of the off-surface points by moving the points over the surface along the normal direction. So when you basically move the points over the surface to the outgoing direction to the object, the 3D the surface, then we are basically assigning some kind of the positive, the plus, the signed distance. And if we move the points to the inside of the shape, then we are also assigning some kind of the negative design distance. So by having this kind of the non-zero distance kind of the constraints, we can basically calculate also the non-zero weights for the radial corners. So this was the basic idea in terms of that we are doing some kind of the global fitting of the impulse function, the sign distance function, with some kind of all the kind of the points as kind of the constraints in terms of solving this problem. And this problem was basically solved by just like making some kind of linear system. So when you basically define this kind of linear system, we can basically calculate the weights for all the points that we have, and that basically defines the implicit function. So this was the idea. And also the other thing was that when also we have the surface normal information, we could consider basically using this information to also approximate the first order the moving least square the equation into slightly different way in terms of that we are not solving the least square the problems in this case. Sorry, not the eigenvector the problems in this case, but simply basically replacing the variable of the surface normal for the query point into the surface normal into the other points using some kind of the pre-fitted the tangent plane the information using the pre-computed the surface normals for all the points. So by replacing this kind of the normal information, what we could achieve was that now we don't need to solve the eigen the vector problem, but we can simply calculate all the function values by just calculating this function. Which becomes like even much faster to calculate all these kind of the function values. So these are basically all the ideas in terms of that how we can do some kind of some conversion from the point cloud into the impulse function, basically the sign the distance function. So we also discuss some kind of the comparison in terms of like when the moving least squares would be the better, and also in which other the cases the radial the basis function would be better. So let's quickly try to basically fill in this table and see like what's the kind of the pros and the cons of each of the cases. Okay, so if we see the table here, then obviously the fitting of the moving least squares is about like doing some like local fitting, right? Based on some kind of the weights, which is defined with some kind of the weighted function that we are defining, right? So the moving least square was more about the local fitting, while the radial basis function is more about sort of the global fitting. Basically finding the optimal the set of the weights for all the points by solving the least square problem for the entire points, right? So the fitting for the moving least squares is like local and the global, right? And the moving least squares is not typically not requiring the surface normal information, but actually the moving least squares is basically typically being used for the surface normal estimation. But for the radial basis function, to avoid the trivial solution, the typical approach is to basically use the surface normal to basically have some kind of the off surface the points, right? So the surface normal information is typically required for the radial basis function. And the computation time of the moving least squares would be basically way faster because it's local fitting, and the radial basis function would be much slower because it's like solving the big linear system. And the moving least squares would be the more robust to the noise because it's not basically being affected for all the points given the point cloud, but while the radial basis function can be more sensitive with some small noise because it's solving the global optimization. And also typically the radial basis function, the output is smoother. It's also because of that the representation, while the moving least squares may not be that smooth, but it also depends on like how much basically the many of the orders of the polynomial the terms that we are going to use in the fitting the process. And since we are also using the global the optimization, typically the radial basis function can better capture some kind of the fine details, while the moving least squares may not be able to capture some of the fine details. But this is not kind of the absolute kind of things. It all depends on how we define all the parameters and make some kind of the details in the implementation. But these are some kind of the higher level the ideas. So what's going to be the good and bad things for each of the kind of the techniques. So typically, when you want to basically achieve some kind of the good quality of the implicit function, when you also assume that the input point cloud is basically very dense and also basically the noise free. The best way here would be basically using the radially basis function because it's more about doing some kind of the global optimization. But still, the global optimization of the basis function is still limited to only basically optimizing the weights for each of the radial the corner for each of the point. So it's basically not exactly directly optimizing the function, the output, the values, but more about basically optimizing some kind of the parameters for the input function, which is the weights for each of the point. So the kind of the technique that we are going to discuss, mainly discuss for today, is about some kind of the even better way, doing some kind of the also the global optimization, but not for some kind of the parameters to represent the final the input function, but directly optimizing the function values defined for each of the center of the voxels in this really great. So this is basically the basic the things that we are going to discuss. So the technique that we are going to briefly talk about today is this technique, which is the Poisson surface reconstruction. So here the thing is that given some kind of the oriented point cloud, which means that we have the point cloud with the surface normal information. So when the surface normal information is given, or can be estimated using the moving least squares or something, how can it directly get the implicit the function, not some kind of the function with some kind of the representation, but directly getting some kind of the function values at the center of the voxels. So this is basically the technique that we are going to discuss for today. And the Poisson surface reconstruction is basically the technique which is like widely used for many kind of the cases that we are converting the point cloud into the implicit function, especially in the case that when you want to get the best quality of the implicit function, because it's kind of the nature of like doing some kind of the global optimization directly into some kind of the values that we want to get for each of the box of these centers. So we are going to discuss this technique for today. And the basic idea for the Poisson surface reconstruction is that the key observation here is that we are seeing that the gradient of the signed distance function that we are going to get at the end should be the same, basically aligned with the surface normal information, right? And we have seen that basically how we can basically get the surface normal information, right? So then the problem basically becomes that, what we basically want to do is that we want to find the function which derivative becomes the same with the surface normal, right? So this is basically the problem. Like, so given the kind of surface the normal information, we do like a function which the derivatives become the same with the surface normal information. So here the question is that how we can find such kind of the function, right? So the kind of the simplistic idea that we can think of in terms of like finding such kind of function is that given the vector field, so here the vector field is basically the surface normal information defined for each of the points, right? Given the gradient, the information, we can just consider like taking the integral of the kind of the vector field. Then the output, basically the function should be basically the function that we want to get, right? Then is it okay? Like, do you see any kind of problem with this? So given this kind of the vector field, the problem is that, so whether the vector field always like analytically integrable. So that's kind of the problem. So we are going to briefly talk about some kind of something that you already learned in the vector calculus in the first year with some kind of the basic kind of things here. So the thing is that when you talk about some kind of the vector field in some kind of the 3D space, the vector field may not be analytically integrable. So there's actually condition that the vector field is like integrable. Do you remember, or what's the kind of the condition that the vector field is like analytically integrable? If you remember that you learned from the vector calculus course. No idea. Yeah, so this might be kind of like good motivation that review that you learned from the vector calculus. So basically the thing is that not all the kind of the vector field is like integrable. The integral, the kind of the vector field is kind of the curl-free the vector field, which means that when you calculate the curl, this from the given the vector field, it's basically the zero for all the points in the space. Then that's the vector field which is integrable, which means that that's kind of the vector field that we can calculate some kind of integral of that. And this is kind of the case that we also call that is the conservative the vector field. So which means that not all the vector field cannot be used for some kind of taking the integral. So that's kind of the issue. But the thing is that since what we are basically getting is that we are getting some kind of the implicit function of the 3D shape, which basically, so the surface normal information that we are basically getting should be the gradient of some kind of the target, the implicit function that we are getting, right? So ideally, in the ideal case, the input the surface normal information should be basically a conservative the vector field because actually it's coming as some kind of the gradient of the implicit function that we want to get. So in the ideal case, there should be no problem in terms of taking the integral. The problem is that we are basically also estimating the surface normal information. So it means that there might be some kind of the noise. This may not be the perfect the gradient information of the function that we want to get. So when you have some kind of this small noise in the surface normal information, this might basically affect in terms of the vector field becomes like non-conservative vector field, which means that we cannot directly calculate the integral of that. So that actually happens in the most of the cases. So here the question is that in the case that we cannot directly take the integral of the vector field, so what should we do? So that's kind of the problem here, right? So in the cases that like when you have some kind of the arbitrary vector field, whether we don't know whether the vector field is the conservative or not, what we can do is that we can consider basically solving a least scarcity problem again, but in the continuous the space. So let's think about this kind of case. That what we are basically doing now here is that we are basically solving this kind of the minimization problem. In terms of like when you find the function f here, which the derivative, the difference between the derivative, the function that we are getting, and also the input vector field, this difference, the squares of this difference becomes like minimized. So that's basically the goal here. So in the 1D case, it's basically identical, but the thing is that this is the case that we're having some kind of gradient information, and we are finding a function f here, which the first derivative becomes the same with the input gradient. So this becomes our kind of the objective function. It is clear? So then now here the question is that how we are going to solve this kind of the least scarcity problem in the continuously setup, right? So how can I solve this? So there can be like multiple ways in terms of like, interpreting the kind of solution for this, and also how we can approach this kind of the optimization the problem. One kind of the way that we can basically consider in terms of like how we're gonna solve this problem is that we are going to quickly see the Euler the Lagrange formulation. So this is like very general kind of the formulation that can be applied into the many tons of the application, especially many things in the physics. But here the basic idea is that for any kind of this integral form like this, which is defined with the function L, which is also the function of the some kind of the variable x here, and also the function f, and it's the derivative here. Given any kind of the function L here, the solution, the function f here can be basically obtained by solving this PDE formulation. So basically, the kind of the some stationary point of like this integral, either some kind of the minima or the maxima of this kind of the integral here, and also basically the function either minimizing or the maximizing this integral function here can be obtained by solving this PDE formulation. So that's the basic idea for the Euler-de Lagrange equation. So given this kind of the idea that we have some kind of very general form of the formulation that can be applied to the many kind of the cases, here what we are going to do is that we are going to apply this idea into this minimization the problem. So let's not think about some kind of the high dimensional case for now. Let's only think about the 1D case. So we are going to basically find function f here, which is like minimizing this. And we want to basically interpret this function into this form of the Euler-Lagrange equation in a way that we can find the solution function f here, maximizing this as kind of solution of like this PDE formulation. Make sense? So here the question is that given this minimization the problem, I recommend you to take the snapshot of like this. So given this kind of the minimization the problem, how we can define this like function L here? And then based on this, the definition of the L here, how we can also get some kind of the solution, the function, the F here, based by solving this PDE formulation. So let's quickly try to do this. So try to define the function L here, which is basically minimizing this formulation, the least scarcity formulation. And based on that, let's plug in this L into this PDE formulation and see what's kind of the equation, the function f here obtained as kind of the solution of this PDE. So yeah, let's see step by step. So basically, given the least scarcity problem, we can define the function L into this way, right? So the function L becomes the least scarce itself, right? So given the L function, if we take the derivative like this function L or with respect to the function f and the f prime here, then we're gonna get these two terms, right? We can also take the derivative with respect to the x here, then we basically getting this. So when you just basically plug in all the things into the PDE that we have, then what we can see is that like the solution, the function f, should basically have this kind of the relationship with the given the vector field the G here. So basically what we can get is that when you so this is basically the relationship that we are getting. So the second derivative or the output the function df that we are going to get here should be the same with the first derivative of the given the gradient function. So if we find such kind of the function, which is second derivative become the same with the first derivative of the gradient function, the g here, that's basically the function that we want to get, which is basically minimizing the L2 difference here. Make sense? So this is basically some kind of the explanation for the 1D case. Basically, how we're gonna solve the least scarcity problem, which is basically based on this kind of formulation. The thing is that we are not basically reconstructing the implicit function not in the 1D case, right? Typically, basically in the 3D case. So in the 3D case, the corresponding the formulation is basically this. So when you have any kind of a high dimensional space, the function f, which is basically minimizing the L2, the security, the difference, is basically the function which is satisfying this. So when you take so instead of like taking the second derivative, so now we are taking the Laplacian of the function here, right? So when you take the Laplacian of the function here, that should be basically the same with the divergence of the gradient, the field, the vector field in this case here. So that's basically the output function that we want to get. Makes sense? So if we can basically solve this kind of the formulation, that becomes some kind of the optimal sign distance function given the surface normal information. So here the thing is that if we so what's this kind of the function? So if we see that actually the divergence of the vector field here is some kind of the scalar function in the space, then the function that we are solving basically having this kind of form. So this is basically the formulation that we are going to solve. So in terms of that, we are finding a function which Laplacian becomes some kind of the given some scalar function in the space. And solving this kind of the problem is actually this kind of the formulation is typically called the Poisson's equation. And we're going to also briefly see in the next the rest of the lecture that there are actually quite many applications of this like the Poisson's equation. So you can see that actually the problem, it turns out that given the surface normal information, we are taking the divergence of this kind of the surface normal information, and then if we are solving this like Poisson equation with respect to like getting the sign distance function from the surface normal information. So this is basically why we are calling this equation, this kind of technique as kind of the Poisson surface reconstruction, because we are doing some kind of the surface reconstruction by solving this Poisson's equation. Make sense? Any questions on this? So now we can see basically how we do some kind of the global optimization of the function with the given the kind of the normal information given as the vector field here. And here the question is that how exactly we are going to solve this, how we are going to basically implement kind of the solver for this like the Poisson's equation, right? So more specifically, we want to basically solve this kind of Poisson equation in a discrete setup, right? So once we basically discretize the 3D space into the voxels in the space, how we are going to calculate this kind of the solver for the Poisson's equation. So actually, like the implementing this solver in this 3D space is not that easy task. It's like quite complicated. So we're gonna see first the 1D case. So in the 1D case, what we are basically doing is that we are dividing the kind of the 1D kind of the domain into some kind of the samples in the space. So let's say we are basically having some kind of the consecutive the points over the 1D space with the same uniform the interval across the kind of all the points. So let's say that we are having the xi, which are basically the points over the kind of the 1D space. Then what we can do is that now the function in the space can also be represented as a vector. Basically, when you evaluate the function for all the sample points over the space, now we can represent the function as those kind of the function value at the sample the points. That becomes a vector in the space, right? So what we now do is that we basically represent the space as kind of a set of the points, a sequence of the points, and then the function also becomes the vector, which is the values that are basically obtained by evaluating the function for all the points, right? So in some visually it becomes like this. When you have some kind of the function over some kind of the 1D space, we are taking some kind of the discretized, some kind of the a set of the points with some kind of the uniform interval in this case, and then evaluating this function, and basically the function value becomes a vector here, right? So given this kind of the vector representation of the function, and also in the discretized space, what we want to do is that we want to compute the first derivative and the second derivative, right? So how we can calculate the first derivative of the function for each of the points is that we can basically simply approximate the derivative like this, right? So actually, there can be some slightly different kind of the ways to approximate the gradient. But the simplest way might be is that we are taking the two the function values at the consecutive the points. So given for some kind of the point xi here, we are taking the function value at the xi and also the xi plus 1, and taking the difference between these two and dividing this by the interval between these two, right? So that's kind of the one very simple way to approximate the first derivative. And what we can see is that actually this like function, the gradient, the computation can also be represented into the kind of the vector, the matrix, the multiplication the form. By having this kind of the formulation, we can give some kind of the vector, the form of the function. Now we can calculate the derivative like in this way. So actually what you can see is that not only for the gradient at one specific the point here, if we want to compute the gradient value for all the points that we have in the 1D sequence, actually all the derivative in all the points can be computed by like one large the matrix the multiplication. So let's think about that. We are having the given the function, the vector here, basically the vector form of the function here, and defining this kind of the large the A matrix, which is basically playing the role as basically computing the gradient of the function. So basically by multiplying this like big matrix and the function value here, what we are getting is that some kind of the approximation of the first derivative, the gradient in the 1D case, right? So we can see that the f and the g here is the discrete the approximation of the function the f, and the g here basically becoming some kind of the first derivative of the function f here, right? And the matrix A plays the role as basically computing some kind of the gradient of the given the function. So this is kind of some kind of the discrete the form of all the continuous some kind of the functions and the operations. Make sense? So from the continuous to the discrete some kind of representations, we are seeing this kind of the correspondence. So the function in the continuous space is like all represented as kind of the vector in the discrete space, right? And for the operator, now we are seeing that the taking the derivative is basically kind of the operator in the continuous space, which is now represented as kind of the matrix form in the discrete space, like this. Right? And also, like when you apply this like operator into the one specific function, the output also becomes another function, which is the gradient in this case, right? That also should be represented with the another the vector in the discrete setup as well. So we are seeing some kind of the correspondence between the function to the vector and also the operator to the matrix. And when you apply the operator to the function, the output also should be another function, right? That also should be represented as kind of the vector. So we are making this kind of conversion from the continuous to the discrete setups. Make sense? Any questions on this? And obviously, we can do the same thing not only for the first derivative, but also for the second derivative as well, right? So when you basically want to calculate the second derivative like this, then it's this. We are doing the same thing. Like we are taking the difference between the gradient the values for the two consecutive points, dividing this by the uniform the interval the length here. Then this also can be represented into this kind of the some vector the multiplication form, which means that now the second derivative also can be represented into the another matrix form like this. Actually, this also can be represented some kind of matrix multiplication of the first order kind of the derivative as well. So basically, this is the same thing. Now the second derivative operator is represented into the another matrix form. And then also the output also is represented on the vector form here. So we are basically doing this kind of the some discretization in terms of that the function is represented as the vector and the operator is represented in matrix. So this can be done for all the kind of the operator and the function that we have, which means that given the Poisson's equation that we are finding the function f here in a way that the second derivative of the function becomes the same with the first derivative of the given the gradient function here in the 1D case, we can basically discretize this kind of setup by defining the second derivative the matrix here and the first derivative the matrix here. Then this becomes basically solving some kind of the linear system. Make sense? So we have some kind of given the gradient function, the input gradient function, which will be converted into the vector form here. And the first derivative, the matrix A, and also the second derivative, the matrix L, these are some kind of the given information. So we can pre-compute these two operators. So these are basically not dependent to the input information. These are basically defined based on our some kind of the discretization of the space, not for the function, right? So given this kind of the two operator, which is not dependent to the input function, input the gradient function, this G is only the information which is like given some kind of given information, the input information for some specific function. We are finding this like the vector f, which is the function values at each of the sample the point, right? So this becomes like typical the linear system, right? It is clear. But here the question is that, so would the solution be unique in this case? What do you think? Would there be some kind of the solution and it would be the solution be unique in this case? Yeah, so I recommend you to check how exactly we define the L function in the previous slide, which is basically like computing this way. But the thing is that for the endpoint of the space, we cannot basically calculate this kind of thing, right? So because we need some kind of the two, basically the points near that each of the required point, which means that actually the Laplacian cannot be the full length matrix because we are not having the information at the end, right? So the thing is that given the L matrix becomes some basically non-full length matrix, which means that there is basically no unique solution. There will be the infinite the number of the solutions, right? So basically what we can see is that given the any function the f here, if you basically add some kind of the constant number for all the points in the space. So when you have some kind of the function the f here in the 1D space, whether you basically add some kind of the constant number or the subtract some kind of constant number, basically moving the kind of the graph of the function to the upward or the downward, it is not basically changing the second derivative, right? So the derivative, the first or the second derivative of the function is basically not being changed when you basically move basically upward or the downward of the function, right? So which means that when you basically add any kind of the constant number into the given the function, that will also satisfy this equation. So that basically shows that there is no unique solution for the output function f here. So which means that we need some kind of the extra the constraints to basically specify like one unique function, right? So what we kind of be some more information that we can use? Any thoughts on this? So far, what we are discussing was to basically utilize some kind of the given the surface normal information in a way that we are finding some the signed distance function, which first derivative becomes close to the surface normal information, right? But there is information that we didn't use yet. Any thoughts? Any idea? So the only information that we are using was the surface normal information in a way that the derivative is aligned with that the normality direction. But the other information that we also know is that the sine distance function, the output function that we want to get, the function, the value, the output value should be 0 at the position of each of the sample point, because like those are the points sampled over the surface, right? So we are actually not only having the information about the derivative of the function, but the function, the value itself for some of the sample points. That should be actually some kind of that's basically the additional information that we can use as some kind of the additional the constraints for this kind of the linear system. So given this kind of like the linear system, actually we can consider adding some kind of the additional some kind of the constraints in terms of that the function value becomes close to 0 for the points that we have over the surface. So that's kind of the problem that we are going to solve. Makes sense? So we are basically having the two terms here. The first term is about the least squares, about the surface normal information, which is basically is turning into the linear system in the discrete setup. But we also have some kind of the constraint that the output function value to be close to 0 for the sample the points that we have. So we are basically minimizing these like two terms in terms of the given the function here. And when we also have this kind of the additional the term for the function value, the output itself for the sum of the sample points, this equation is called the screened the Poisson the equation. So that's why you also see that some kind of extension of the Poisson surface deconstruction into the screened the Poisson surface deconstruction. Make sense? But you can see that this is basically nothing but we are basically utilizing this like the two information. Like one is that the function value should be 0 at the points that we have the samples here, the over the surface. And also its derivative also should be aligned with the surface normal information, which is turning into the linear system in the discrete setup. And so in the 1D case, this is really kind of like doable in terms of like we can easily implement the matrix for the first derivative and the second derivative here. But if it goes into the higher dimensional space, it becomes a little bit like complicated. So we are not gonna get into all the details in terms of how we're gonna implement this in the high dimensional space. But the high level, the idea is that for each of the gradient and the divergence and the Laplacian, we can basically consider defining some kind of the big matrix in a way that basically making some kind of the matrix form corresponding to each of the operator in a way that we are basically turning the Poisson's equation into the solving the least square the problems into the matrix form. So that's basically the high level idea in terms of like the context function becomes the discrete vector, the operator becomes the matrix, and the function composition becomes like the matrix the multiplication. And the solving all of the Lagrange the equation becomes like solving the least squares into the matrix form. So in the implementation, basically typically what we do is that we given some kind of the set of the points with the surface the normal information in the 3D space. We first define some kind of the 3D grid. And for the center of each of the voxel, we are basically getting some kind of the vector field information, the gradient of the output, the gradient of the output, the function, the information by aggregating some kind of the points inside the voxel, right? So given some kind of the oriented point cloud information, we basically calculate the vector field for each of the center of the voxels. And then we are basically computing the divergence with some kind of the operator that we are defining. And based on that, now we can solve the Poisson's equation by solving the least square the problems. And once you basically get all the kind of the function values at the center of the voxels or some kind of the corner of the voxels, based on that, we can now extract the isosurface, the zero level set, the points in the space. So this is some kind of the higher level the idea in terms of like how we exactly do some kind of the global optimization. And then I also recommend to try to think about basically how we can really extend this kind of the idea into from the 1D to 2D and the 3D. So what should be some kind of the divergence the matrix or the Laplacian the matrix exactly in the 2D and the 3D space. That is like way more complicated with the matrix that we are defining in the 1D case. But it's kind of like some doable kind of the task. Any questions on this? So as I said, actually, this Poisson's equation has lots of the applications in not only for the 3D, but in many kind of the field. Actually, one of the interesting some kind of the applications that I'd like to briefly mention here is that it can also be used for many kind of the 2D image applications. Like one kind of the application is basically the image editing. So here the question is that what kind of numerical methods are used in the calculation of the Poisson's equation? Well, I mean, in the calculation of the matrix, it does not require any kind of the numerical method. It's just like method like how we're gonna basically make some kind of the matrix for each of the operator for the divergence, the Laplacian, as we have done in the 1D case, we can basically define this kind of the matrix. And the rest of the part is simply just solving the least squares. It's the same kind of thing. but it will be basically very giant, the linear system with lots of kind of the voxels there. So there are some kind of the numerical techniques in terms of like how we're gonna make it more efficient in terms of like solving the linear system. So if you are more interested, you can also check out the original paper into the technique, which is basically introducing some kind of the resolution degrees kind of solver in terms of like solving this kind of like linear system. We are not gonna get into that here. So coming back to some applications, actually, there are lots of the applications for the Poisson's equation. Like one interesting idea that has been introduced like more than 20 years ago is basically about this kind of like image editing. So here the idea is that we are compositing some kind of the foreground region here, the dog and some kids here in this image into the background image here. This is also taking some kind of foreground region here, like eye, nose, and the lips here, into the other image like this, right? So here the question is how we can seamlessly basically composite this kind of like foreground region from the other image into the background region into this image, right? For those kind of the tasks, now we can just like use some kind of some AI model for this, but like more than 20 years ago, there's no even no neural net, nothing we can do in terms of doing some like deep learning. But still, we could get this kind of results with some kind of the simple like calculation of the like linear systems. And the basic idea here is that actually we are not taking the the values themselves in the foreground region, but taking the gradient information. We are only taking the gradient information, the vector field here. In terms of that, we are basically reconstructing the function of the output image here. In terms of that, the gradient of the foreground region becomes the same with those kind of the dog and the kid images, while the function value themselves should be the same in the background region. So we are taking the gradient information from the foreground region, but taking the function value, the boundary condition of the function value itself from the background region in a way that we can do some kind of some seamless decomposition between the foreground and the background. So can you see the meaning like this? So as you can see here, like we are fixing the color values and some kind of the boundary of the foreground region, while basically filling the values inside of this region in a way that its gradient is aligned with some kind of gradient that we have from the other image. So you can see that the tone of the output image is kind of like is the same with the background region, while some kind of the gradient information is coming from the foreground here. Make sense? So yeah, this is kind of one of some kind of application of the Poisson's equation, not in the 3D, but also in the 2D case. So like the Poisson's equation is basically very widely used, and the Poisson surface reconstruction is also kind of the sort of the standard technique in terms of the point cloud into the implicit function deconversion. The only downside is that basically it obviously takes like more computation the time because it's solving the big linear system, and also it relies more on the surface the normal information, which means that the surface normal information should be very accurate without some kind of the noise there. And also the point cloud should be basically dense enough to compute those kind of things. So in case that when you have some kind of like very dense point cloud with quite accurate the normal information, and if you don't care about the computation time, then you can consider using the Poisson surface reconstruction. But otherwise, you can also consider using the moving least squares or the radial basis function. That's the basic idea. Any questions on this? And one quick remark is that actually there is also like bunch of ways in terms of how we can solve like this kind of the Poisson's equation in a like more efficient way. So we are not going to get into some more details, but actually the Song-Yu Peng, who also gave the guest lecture in our course, was introducing some kind of interesting idea in terms of that we can solve this kind of Poisson's equation using some kind of a spectral method. So after like converting everything into the spectral domain, now we can solve the Poisson's equation in a like a much faster way. And this is also kind of the things that we can easily utilize some kind of the GPUs in the calculation of the potential equation. So this can also apply to in many other applications, like fitting some kind of the 3D shape into some kind of the so given information, which is also not only giving the implicit function, but giving some kind of the oriented point cloud as the output as well. So there are some kind of the interesting ideas in terms of like how we're gonna solve that the Poisson's equation. And also there are some neural methods as well, not just like doing this kind of like linear, like solving the linear system, especially in the case that when you have some kind of the noise in the given the point cloud and also noise in the surface normal information, we can also, there are some kind of techniques in terms of utilizing some kind of the neural network to get some kind of the much more like the precise the outputs like this. So you can check this out if you are more interested. Okay. Any questions on this? Yeah, so these are some kind of the techniques in terms of like how we're gonna convert the point cloud into the signed distance function. And the another the missing bridge across the representation was the conversion from the voxels into the mesh. So we're gonna briefly get into the simplest idea in terms of like voxel to mesh the conversion, which is also very widely used. So here the basic idea is that given some kind of the so implicit the representation, typically some kind of the occupancy the information, we are going to get some kind of a triangular the mesh that approximates the surface like this. So while we are talking about the sign distance function in the previous slides, we know that we can easily convert the sign distance function into the occupancy field, right? So here we're gonna basically assume that the implicit information is now the occupancy, the information for the corner of each of the puzzles. So before we get into the 3D case, now we are going to briefly see the 2D case. So when we see the 2D case, this kind of technique is now called the marching squares. Basically, marching is basically like moving forward in the with the squares in the 2D space. And this technique is now called the marching cubes in the 3D space because now we are doing some kind of the marching with the cubes with the voxels in the 3D space, right? So if we briefly see the idea of the marching squares, the basic idea is that we are having some kind of implicit function, which is indicating whether each of the corner points is basically inside or the outside of the 3D shape, in the 2D shape here, right? So basically what we are going to do is that we are going to discretize the 2D space like this with the corner points like this. And then evaluating this function in terms of like we are classifying whether each of the corner points is the inside or the outside of this, the 2D shape. Right? And based on that, what we are going to do is that we are also going to classify like which edge of the grid here should be basically having some kind of the boundary of the shape. So like for on which the edge of the 2D grid, we are having the boundary of the shape in a way that we should have some kind of intersection point like this. So you can see that if we see the two endpoints like this grid edge, like one is inside and the other one is basically the outside, right? Which means that there should be some kind of intersection point between the border of the surface and the grid edge here, right? So we are basically finding all the grid edges, which like one of the endpoint is the inside and the other the endpoint is basically the outside. And for those edges, we are basically finding the intersection point here. Right? So once you basically have like all the intersection the point, the last basically the task is basically connecting those kind of the intersection the points in a way that we are making the contour in the 2D case. Makes sense? So this is basically what we are going to do. So simply what we can do is that given this kind of some like the function value, especially some signed distance value for each of the 2 points, we can easily find the intersection point with some kind of the linear the interpolation. So given the function, the 2 function values, taking the linear interpolation and finding some kind of the point where the signed distance function becomes 0, right? So finding those kind of the intersection points. And the question is that how we are going to connect those kind of the two the intersection points, right? So here the simplicity idea in terms of like connecting those kind of the intersection point is that we are not going to see the all the 2D the cells like all together. We are going to treat each of the cells separately. So let's think about that. We can consider like all the possible cases that we are having the either the inside or the outside the corner points for each of the four corners of each of the 2D cell, right? So if we consider like all possible the combinations of the inside and the outside for the all the corner case, how many cases do we have? Yeah, we should have the 16 cases, right? Because it's the 2 to the 4, right? For each of the corner point, there are the two cases, like we have four corner points, then we have the 2 to the 4, like 16 cases. So these are like all the 16 cases actually, right? So given these 16 cases, for example, here, there should be no intersection point with the boundary of the shape and also the edges here, right? So there's nothing to draw in terms of like drawing the edges here. And this is also the same. There is like nothing to draw because like all the points are basically the outside here, right? So there are some cases that we might have some kind of intersection point here and the here. So let me just switch into the region here. Yeah. So you're gonna have the intersection point here and the here. Then we need to draw some kind of the edges here, right? This is the same. Here we're gonna have the intersection point here and the here. Then we're gonna draw the edges here like this, right? So the basic idea is that we won't just basically see like all the 16 cases like individually and try to basically draw some kind of the connection, the lines for the intersection, the points. But the thing is that basically even we don't need to consider like all the 16 the cases because there are quite many some symmetric the cases as well, right? Uh, So basically, by doing some kind of rotation, like all these cells, we can see some kind of some groups. For example, like this is the case that we are having these three kind of the points, which are basically like having like one, basically, for example, like the negative sign, and the other point is basically positive sign right here, right? And if we rotate this, then by rotating this kind of the cell here, we can also get the third one here as well, and also this one and this one, right? So if we see like how we can basically connect the intersection points in this case, then we can basically see how we can also make some kind of the connection the edges for the rotated cases as well, right? So we can see that these are some kind of the same D cases with some kind of the rotations. Or there are some cases that we are also having the flipping as well. Like so, this is also some rotation the case, and this and the other, yeah. So these two are basically the same case, but we are just like flipping all these signs, right? But like flipping signs should not change the connection, the edges. Still, it's basically having the two intersection points here and making the edges here as well, right? It's the same also in this case. So basically, as you can see, like based on this kind of like some symmetric the relationship or some kind of flipping the relationship, we can group like all these like the 16 cases into all the equivalent kind of the cases. Then at the end of like all the grouping, we are seeing like all these kind of the only those like the four cases. Make sense? So after the grouping, we're gonna see all those like the 4D cases. And for the first case, we can say that there is nothing to draw, right? So no intersection point. So there's no edge here. And this is the case that we're having the two intersection point here, then we're gonna draw the edges like this, right? And this is another case that we're having the two intersection points and drawing the like single edge like this, right? And this is kind of some problematic some case because we are going to have the four intersection the points on the all the edges here. And here the question is that how should we basically connect those the intersection points? How should we do that? So which means that there are some kind of the ambiguity. We can make some of the edges like this way, or the other way, right? Like this and this. So there are some kind of some ambiguity in this kind of case. So for such kind of cases, like some simple solution is that we can try to basically divide the cell into the even the like the smaller basically the 2D cells like this in a way that so we are basically increasing the resolution of the grid until we do not see any kind of this kind of the ambiguous cases. Or the simple solution is that we just pick randomly like one of those kind of two cases. So these are some kind of some simple solutions, right? Makes sense. So this is like very simple the idea in terms of how we're gonna basically like make some kind of the final some kind of the 2D contours with some kind of the connection of the lines. And the thing is that we can do the same thing for the 3D case as well. So in the 3D case, how many kind of the cases do we gonna say in terms of like having the inside and the outside for the corner points? How many combinations do we see? Question? The 2D case, like we have seen like 16 combinations, right? And after grouping, we could see like four like equivalent some kind of the groups, right? In the 3D case, now we are having the 256 cases because we are having the 8 corner points. Each corner point has some kind of inside, outside. So it should be 2 to the 8, 256 cases. And once you also group like all the equivalent kind of the cases, so these are actually some kind of the some representative examples for each of the groups. And you can see that after some grouping all these symmetric cases, now we are seeing some 15 groups like this. So which means that for any kind of the some one of the 256 cases, we first need to say that in which group this specific combination like falls into that, right? Then based on like for each of the groups, we can first basically predefine how we need to create some kind of the triangles based on the intersection point that we have. Then we can basically construct the triangles in this way. So yeah, and those are some, also there are some kind of the cases that we are having some kind of ambiguity. And if we have the ambiguity, then we can consider like, increasing the resolution, basically dividing these 3D voxels into the smaller the cells, or we can basically choose one of some kind of the randomly choose like one of some the ambiguous cases. So this is kind of the simplest idea in terms of how we convert the voxels into the mesh. The good thing like this idea is that this is like basically very simple to implement. It's all about basically predefining some kind of the ways to like try and make some kind of triangles from the given the intersection the points, and just like doing some kind of classification, right? So it's basically easy to implement relatively compared to some kind of other the complex the cases. And the most important thing is that it's basically treating all the cell like individually, right? So everything basically can be run in parallel. So which means that we can basically accelerate this kind of computation using the GPUs. So that's really kind of the good thing. And also this is like the parameter-free way. So there's nothing to basically tune in terms of tuning some kind of parameters. So it basically lots of some kind of the advantages. Obviously, there are some kind of the disadvantages as well in terms of that there is no guarantee in terms of the topology, right? So we don't know how those triangles will be basically connected across all the cells, right? So there can be some kind of some weird some kind of connections across all the triangles over the entire space, the shape, the space actually, right? And also there can be some kind of the failure cases like this. For example, like for this, what we want to get is that we want to get the sharp edges across along this line, right? So that's the ideal, the output here, right? For the cases like when we have the cube like this, we want to have some kind of the straight the edge along this line. But depending on how we define some kind of the 3D grid, the 3D the cells, we may not be able to basically the mesh edges, which are really aligned with this kind of the sharp edges. So there are some kind of the downside for this idea as well. But actually, this is kind of the most widely used some kind of the technique in terms of converting the voxels into the mesh. And one funny thing is that actually this idea was first introduced in the 1990, of course, around that time, so which means that it's like more than 30 years ago. And it has been patented for the decades, which means that we could not use this kind of technique for many commercial the software. So to avoid the patent, the other some kind of the technique was that we are doing the same thing, not for the kind of the cube like the cell in the 3D space, but we are dividing the 3D space into the tetrahedron like this, and then doing the same thing for those kind of the tetrahedron, not for the cubes. Then we also need to define this kind of the some all the possible the combinations of the sign distance, the values for all the corner points, right? So this technique also can be applied into the not the cubes, but also to the tetrahedra as well. So this is the technique which is called the merging tetrahedra. Okay. So that's it. So this is basically some kind of technique, and also the assignment 4 will be basically about implementing both of those things. So we will need to implement the implicit the moving least squares and also the merging squares as well, in a way that you can basically convert the given the oriented point cloud in the 2D space into the final some kind of the contours in the 2D space. So you will get into that basically and see how we can do this kind of conversion in the code. Okay. And this is basically concluding our discussion on basically how we do all the conversions across the representations. Now we can see that the point cloud can be converted into the implicit function using either the moving least squares or the regular the basis function, or we can directly convert point cloud into the voxels using Poisson surface reconstruction. And once you basically have the implicit function or the voxels, then this can be converted into the mesh using the merging cubes, right? So these are not only techniques for the convergence, but these are some kind of the representative techniques that are widely used for those kind of convergence. And if you have any representation of this 3D data, now we can say that we can convert that into the all other the representation using those kind of techniques. And this might be actually quite useful for your the project as well. When you have some kind of some random some 3D the data, you might need to do some kind of the conversion into the other representations. Okay, so this is like concluding our discussion for the representation deconversion. The last topic that we are going to discuss in this class will be about the meshes. So actually, as we discussed in the first lecture, the mesh is also the widely used representation for many applications, but especially the mesh is really good representation for the manipulation. So after doing this kind of conversion, we're gonna see how the output, the mesh can be utilized in the many kind of this manipulation, the applications. So after we have the guest lecture and the assignment session next week, we're gonna discuss the measurement manipulation in the week after next week. And we're gonna briefly also discuss the 3D generation as well. So this will be basically the end of all the kind of the lectures. Okay. Any questions on this? So as I said, there will be no class this Wednesday, and we're gonna have the guest lecture next Tuesday. So I will see you next Tuesday. Okay, thank you. Bye.